recommend you look into. Alright, so let's see anything. Alright, so 4D diagrams, go into that. Infinite thinness. So infinite thinness is another little thing that's good to clear up, is the idea of, vertices are faces. Those little diagrams, you connect the vertices. And you can kind of, it's the problem with it is it's not very easy to see faces or cells. I'll get into what a cell is. A cell is kind of similar to a face. So infinite thinness, how thin is two-dimensional? We can see that two-dimensional is infinitely thin, but a flatlander would not see it that way. They would see two-dimensional as having length and width. They wouldn't know about depth, so they wouldn't be concerned with it. They would just, oh yeah, sorry, the cube has 8 vertices. It's been a few months since I've done any math because the school system isn't a quarter system. My math skills are really rusty. I remember I got 90s in math and calculus, but if I had to do a problem from one of them, I'd have to look in my books. I haven't done them in so long. Physics problems, though, I've been doing, and those are fine. I'm getting 102% in that, so that's going well. All right, so eight vertices. All right, so infinite thinness. Again, the plane is infinitely thin. Right. Plane is infinitely thin. Not from the flatlander's perspective, but from a 3D perspective, it is infinitely thin. Because once we have that other dimension, from that vantage point, we can see that it's thin. Infinitely flat. 3 dimensions, to us it seems like it has the 3 dimensions, but if you look from a 4-dimensional perspective, it's infinitely thin. And you have to understand that, right? Because if you can, after all, if you can compile a shape out of cross-sections, each of those cross-sections has to be infinitely thin. So if a 3-dimensional cross-section is infinitely thin, that means all 3D things are infinitely thin. Because if you look at that 4th axis, that is perpendicular to our existence, our world and everything, that means that our hyperplane, you could call it, is infinitely thin. So a 4-dimensional object would not be infinitely thin from a 4-dimensional viewpoint, at least. So 3 dimensions is actually flat. You got lied to all that time. Like anybody who told you that 3D is not flat, they're wrong, but they didn't know any better. Most people don't know any better, but 3D actually is flat. It's less flat than 2 dimensions, but it still is flat. Alright, Tesseract and Gloam. Alright, so if we're going to talk about 4-dimensional space, we need to know the 2 most basic shapes. Maybe I'll start with a tesseract. Now, to understand the tesseract, we can look at it as a part of a logical progression of shapes. The first is a point, and we can extend it to have a line. A line has 2 vertices and 1 line segment, obviously. And if we extend the line parallel to itself, we get a square. It has 4 points and 4 edges. And notice these are edges. These edges are the outside of the square. But if we extend the square parallel to itself, we get the cube. And the edges are part of the outside, but we have a new thing that comes into play. We have faces of the cube. There's 6 faces of the cube, and they are the outside. Now, if we want to explain these faces to a flatlander, we'd have to explain to them, okay, so there's these faces of the cube. And we explain to them that the cube is like a 3D square. And they'd ask, what is a face? We'd be like, it's like an edge, but it's 2-dimensional. And we might run into problems with them because they'd be asking, well, it's 2-dimensional, right? But space is 2-dimensional. How do you have a surface that's 2-dimensional? Because they live on 2-dimensional. So it's kind of like face. So getting a ton of messages here. Other things. Alright, so a cell is like a face. Cell. So you got edge, an edge, a face, a cell. So you've got the line, line, square, cube. Tesseract is the next step up. It has 16 vertices, and it has 8 cells, which are like faces, but they're not faces. You see, it also has faces, much like a cube has edges, and it has edges. It has all of those. But these cells are the outside. They are the surface of the cube. And a whole 3-dimensional thing could exist on the surface, much as a whole 2-dimensional thing could exist on the surface of a 3D object. A surface is 1 less dimensional than the object it is on. And now we have to go over an even more basic shape, the gloam, or hypersphere. It's usually called hypersphere, but gloam is a cute little name that it's often called. So now let's start again from the point. This time, imagine you have one dimension. Take every point that is an equal distance away from your central point. You'll have 2 points, one here and one here, and you'll have a line. Now if you do this with 2 dimensions, you will not get you won't get a square, you'll get a circle. And all points on the outside of the circle are an equal distance away from the center. If you do that with 3, you'll get your sphere. So 3 dimensions, you'll have 3 axes of which these points can be on. So any distance, any location, a 3-dimensional hyperplane can be described with 3 numbers. For 4-dimensional space, the same space the Tesseract occupies, it's like that but with an extra dimension. Again, you have the central point and all points in that 4-dimensional space that are equidistant from it, and you'll have a hypersphere or a globe. And that is those are the 2 shapes that you should really know about because they're really important. 4 dimensions at least. In 3D, they don't really exist in 3D. You can't compress them into 3D, just like you can't compress a cube into 2 dimensions. And if you find a way to project it, as I've shown you, you lose some characteristics, and it's not the same. Just as we project the Tesseract into 3D, but it's not the same. Alright, so what about other shapes? So every time you have a new dimension, there are more and more different shapes you can make. So 3 dimensions, we have a bunch of shapes. 4D, we have even more shapes. Although after 1 dimensions, there is an infinite amount of shapes, but you can also look at distinguishable shapes, and you can also look at geometric perfect shapes. So in 1 dimension, there's only 1 shape, that's the line. You could have a point, but that is actually a 0-dimensional shape. In 2 dimensions, we can have a bunch of different shapes, all flat. You have a ton of them. 3D, the same. 4D, you can have a bunch of them as well. But here I'll just be discussing simple shapes.